Hi everyone, my name is Justin Kang, and today I'm going to be presenting our work, Efficiently Computing Sparse Fourier Transforms of q-ary functions. This is joint work with my fellow PhD student, F.A. Ergenbash, and Professor Amir Ali Agazadeh from Georgia Tech, as well as our supervisor, Professor Kanan Ramchandran from UC Berkeley. The motivation for this project really started when we took a look at deep protein models. These are models that use the same transformer architecture that you see in large language models, and they can tell us a lot about proteins. In a sense, they kind of allow us to generate new biological data directly from the model. Now, the problem is that these models operate on sequences in a pretty large alphabet. So we're talking about an alphabet size of 20 for proteins. And we're often talking about sequences of length at least 100 if we're trying to do something interesting. So we need new tools to deal with this enormous dimension and to help us process and interpret what we get out of these models. One of the things we've been looking at to deal with this massive amount of data is actually the Fourier transform. This is a simple example of a green fluorescence protein. So what we've done here is plotted the brightness as a function of the protein. So we've sort of enumerated over many proteins. And this function looks pretty complicated. But we find that if we take the Fourier transform, it's in fact quite structured. So the transform is sparse. That is, a lot of these terms are zero. And those that are non-zero are sort of concentrated on suitably defined low frequency. So in this high frequency area, there's no mass. Obviously, these are not the traditional notions of frequency, but it's sort of suitably defined. Now, we find that this actually isn't specific to this problem. In fact, almost all biological problems exhibit this sort of behavior due to just the physics of things. And if we were to try to compute this Fourier transform naively, say via FFT, we'd really hit a wall because we'd have this n, q to the n term where q is the alphabet size. So this is something like 20 to the 100. And again, that's a wall that we can't deal with. So we need new tools to help us compute this transform, and luckily we know that we have this structure. So the question is, can we leverage these properties of sparsity and this negligible mass at the high frequencies to help us more efficiently compute the transform? So this is our basic setup. We have some function f. It's mapping a sequence of integers mod q of length n to some real number. What we're interested in is the Fourier transform of that function, and this is how we've defined the Fourier transform. It's sort of like an n-dimensional q-point DFT, and we're going to assume that this function, f of k, its transform, is in fact sparse. So for many values of k, f of k will be 0. Well, for some, it will be non-zero. Ultimately, we're going to assume we have query access to the model. That is, there's some kind of oracle, and given some sequence, it will tell us the function value at that sequence plus potentially some noise, in this case, complex Gaussian noise. And if our spectrum, our Fourier spectrum, that is S sparse, then we want to ask how many times do we need to ask this oracle? That is, what is the sample complexity we can achieve? And also, what is the computational complexity we can achieve with that sample complexity? And these are our results. So in the noiseless case, if we have a Fourier transform that is S sparse, we can exactly recover the Fourier transform with sample complexity order Sn, and in time complexity order Sn squared. Remember, n is the length of the sequence that's input to our function. And of course, this is a high probability bound. And now this is in the noiseless case, that is, our oracle is giving us samples with no noise. In the noisy case, we pay a factor of n in both cases. So for the sample and time complexity, there's an extra factor of n. Just to throw some numbers around to see how much of a difference this makes, we're talking about, let's say, a sparsity of 1,000,000 and an alphabet size of q equals 4. Q equals 4 comes up all the time when we're dealing with DNA or RNA. And a sequence length of n equals 20, so something sort of absurdly short. But even in this case, if we look at what we can do, we're already something like 5 orders of magnitude difference between the traditional FFT. So the traditional FFT is not viable from a sample and computational complexity perspective, while our algorithm, which we are dubbing here QSFT, is very practical in both the noiseless and noisy cases. The next question you probably want to ask is, how do we achieve this? The key idea is noting that aliasing doesn't need to be destructive, particularly when the transform is sparse. So this is an example of a random q-ary function, and we can take its Fourier transform. In this case, the Fourier transform is not sparse. That's because it's just a random q-ary function, but it'll be useful to look at a dense transform for once to sort of explain how aliasing works. Ultimately, what we're interested in is we want to compute the Fourier transform of this function by just looking at a few of the values. So what I've done here is subsampled this function. So just kept a few of the values here. And if we want, we can take the Fourier transform of this subsampled function. Now, if we take the Fourier transform of the subsampled function, we find that it's actually related to the Fourier transform of the full function in the following way. So a bunch of the values from the full function get summed together, binned together in a way, and then correspond to a single value in the subsampled function's transform. A little more detail here. If we subsample by looking at the range of some matrix M, and this is a matrix that maps from some low dimensional space to some high dimensional space, then the aliasing, which is the terms that get summed together in the big transform, is actually determined by the matrix. So it's all the values k such that M transpose k have the same value. They all get summed together to a single value in the subsampled transform. And ultimately, if the full transform is sparse, then there may be very few terms in the sum that are non-zero. So we would hope that we can reconstruct this function f, the full transform, from the subsampled one. This is a depiction of our overall architecture. So we have some function f, and we're trying to take its Fourier transform. First thing we do is we consider a few different matrices M and subsample by looking at the range of each one. And this gives us u1, u2, and u3. And then we want to take Fourier transforms of these smaller subsampled functions, and that will give us transforms capital U1, U2, and U3. And ultimately what we're going to do is we're going to take these subsampled transforms and combine them together using reconstruction techniques from graph decoding to determine the full transform function f. Thus far, I've been writing the relationship between our function little f and its Fourier representation in terms of this sum. Going forward, just to make things a little bit simpler, we are going to simply just enumerate over all the values of k here and compute f of k and sort of stack them on top of each other like a vector. And we're going to do the same thing for the Fourier transform itself. So this capital F, we can sort of stack all the values on top of each other and also write it as a vector. And the relationship between these two is, of course, linear because the Fourier transform operator is linear. So we can represent that with just this matrix W. In this case, it's the inverse Fourier transform matrix for what we're trying to consider. As a warm-up now, we're going to consider a binary case, that is a sequence of alphabet size 2. So you can think of this as a sequence of +1s and -1s. And in that case, the Fourier transform that we're considering, this matrix W, actually turns out to just be the Hadamard matrix, which you may have seen in other applications before. And this type of transform is sometimes called a Walsh-Hadamard transform. This is a little example of a binary sequence of length 4. And one thing we can always do is just explicitly evaluate that sum. And in this case, let's say there's 4 non-zero coefficients in that sum. These red values there are the Fourier coefficients. And we can write this in terms of ki, which are the sequences over integers mod q. But another thing we can do is write them in terms of this xi, where xi is minus 1 to the ki. Now if we do this, the function has this nice polynomial form. And the Fourier coefficients are simply the coefficients of the polynomial. And now we can iterate over all the possible 1, -1 values for x1, x2, x3, x4, and we can generate some kind of table if we want to by evaluating this function. But ultimately what we're interested in is we want to look at just a few values of this table and compute our coefficients. Now for that function that we're talking about, we have this alternative representation that I was mentioning of the function as a vector. And similarly, we can also have its Fourier representation as a vector. And it's the same thing here as this polynomial, just represented as a vector, and all of these coefficients are in the spots they're supposed to be in. And ultimately, what we want to do is look at just a few values of that function. So first thing we're going to do is subsample. So just keep just these values. And then we want to take the Fourier transform of this small little subsampled function. And as we mentioned before, the Fourier transform of the subsampled function is simply a binning of the Fourier transform of the original function, right? So here we have a 2 here, and it's the sum of the first 4 entries of the full Fourier transform. We get that with the 0 plus 1 plus 1 plus 0 gives us 2. And likewise, this 1 and 0 and 2 are coming from the same place. And we can actually store these observations, this small Fourier transform that we take, in a graph. So we have these check nodes, which represent the Fourier transform, and these variable nodes here that are representing the vector. So we want to use these observations to figure out the values in this vector. And the next step is to just repeat this process again. So we're going to subsample again, keeping just a few values of the function, and then we're going to take another Fourier transform. And because we subsampled in a different way, our binning pattern is a little bit different, but we still have the same general idea where the coefficients of our new subsampled Fourier transform is just a binning of the full Fourier transform. And the binning structure is a little different, so you'll notice that the edges of this graph look a little different, but in general, we're doing the same type of thing we did before, and we store these coefficients in this graph. And the next thing to do is to combine these graphs together into what we call the graph of our aliasing code. And ultimately what we want to do is we want to look at our observations, that is the coefficients of our small Fourier transforms, which are themselves binnings of the full Fourier transform, and do some inference on this graph to determine all the coefficients of that full Fourier transform. Now, there's 3 types of observations we need to be concerned with. The first are the zerotons. So these are ones that are binnings of only 0-valued Fourier coefficients, and they're not particularly interesting to us. The second are the singletons. So these are the ones that are binnings that contain exactly one non-zero Fourier coefficient. And these are the most important to us because they're going to allow us to determine that single non-zero Fourier coefficient. And then finally, we have the multitons. These are ones that involve binnings of 2 or more non-zero Fourier coefficients. And we'll have to do some work with these before we can use them and turn them into singletons. For now, we're going to assume we have this bin identification oracle. This is someone who can look at a bin and tell us whether it's a zeroton, singleton, or multiton. And for singletons, it'll tell us not only what the value is, but also what index it came from. And a little later, we'll talk about how to implement such an oracle. So now that we have this oracle, we can ask them to identify all the bins for us. The oracle has indicated that there's a 1 that's a singleton here. So in fact, that corresponds to this. We can now put the 1 in that circle and also remove the edges that correspond to that circle. And now it's also identified this 2 here being a singleton, so we can put a 2 here and again remove the necessary edges. And now we have this 1, which is also a singleton, and we can remove that. And notice when we did that, we removed some edges that turned this observation also into a singleton. And we see that this is in fact a 1, so we can subtract that off. And now we have fully recovered that polynomial that I showed you all those slides ago. Everything we've been talking about is for the binary case, but everything carries forward to the q-ary case as well with a few differences. So for example, the matrix W now, instead of being a Hadamard matrix, is the q-point DFT matrix, Kronecker product with itself n times over. And a lot of places where we saw -1s before are replaced with qth roots of unity. And of course, now we can have complex values in our Fourier transform as well. So you see here there's some j's around. But otherwise, we do essentially the same procedure. So we subsample, and we take a small Fourier transform from our subsampled function, and we end up with this same type of graph structure. Now you might ask, how do we ensure that this peeling procedure always goes through, that we can always recover the full original Fourier transform? To prove this, we use ideas from density evolution theory. So pretty standard ideas. We construct a Dubs martingale for the number of edges that are still not decoded after each peeling iteration, and make some arguments about expanders as well to ultimately achieve our goal. Now, the two conditions we need are that the number of terms that we subsample each time needs to be of the order of the sparsity. This is to ensure that the number of bins is at least the order of the sparsity. And we also need to take the Fourier transform order 1 number of times, which is important for our complexity bound. And the exact number depends on the sparsity, but we can show that it's always order 1. Now let's return to implementing our oracle. The key idea is using the shifting lemma for Fourier transforms. If we subsample again by looking at the range of a matrix, but now we shift by some vector d sub p, it amounts to a phase shift in our Fourier transform, our subsampled Fourier transform, that depends on the particular index k of the non-zero Fourier coefficient. Now, if we repeat this process with multiple shifts, then we'll get some sort of vectorized observation. And the phase of this vector will tell us a lot of information about k. Now, as we can see, this vector actually looks quite different for zerotons, singletons, and multitons, and this is how we'll be able to implement our oracle. For zerotons, all the terms in this sum are 0, so notwithstanding some Gaussian noise, we expect all the terms in the vector to also be 0. For a singleton, there's precisely one non-zero coordinate. So in that case, we expect all of the elements of this vector to have the same magnitude, and for their phases to coincide with the roots of unity, the qth roots of unity for q-ary alphabet. In this case, q is 5. And then for multitons, because there's multiple non-zero terms in this sum, we end up with phases that are all over the place, as well as magnitudes that are all over the place. Once we know a particular bin is a singleton, the next question is, how do we identify the particular index k? And the answer is by looking at angles of the shifted transform. So by looking at the phases of that vector, we can construct a matrix equation for k. And the matrix that multiplies k actually is determined by the delays that we choose. So one thing we can do is just choose these delays to construct an n by n identity matrix, and we're able to immediately read off k from our observations. And this will require a total of n different delays, giving us our total final sample complexity of s times n. But I promised you that this would also work in the noisy case. So what can we do in the noisy case? Well, in the noisy case, we can simply choose our delays to construct the generator matrix of some code, and then we can just decode that code to recover k. For example, we can choose G to be the generator matrix of a repetition code. And this works well in practice and allows us to deal with noise. So way back at the beginning of this talk, in one of the first slides, I talked about the fact that the Fourier transform of these biological functions was often not just sparse, but also the fact that it had negligible mass on these high frequency components. And in this setting, what we mean by high frequency is actually high Hamming weight for k. So if we assume that k, for example, has bounded Hamming weight for if it's non-zero, then we actually have another approach we can take. If k has low Hamming weight, then this matrix equation essentially becomes another compressed sensing problem, right? We know that k is itself sparse. And so in that case, we can take the matrix D to be the parity check of some t error correcting code. If Q is prime, we can just use an off-the-shelf q-ary t error correcting BCH code. And if Q is not prime, then we can take a look at codes over rings. And ultimately, this is sort of mirrors what I talked about on the previous slide with channel coding. This is sort of a type of source coding that we can implement if we know something about K. And it can further reduce the sample complexity we need to reconstruct our Fourier transform. This is a comparison of our algorithm to lasso. Lasso is L2 minimization with L1 penalization. And as we see here, the complexity of lasso as it scales with sequence length is exponential, and this is a log scale here. Meanwhile, our algorithm, q-SFT as we've dubbed it, is growing linearly in n, and in fact, we have, it looks even less here because this is a log scale, but it's growing linearly in n, and in the regime of, say, n equals 18 here, our algorithm runs relatively quickly, whereas lasso's not even within the realm of being possible to be run here. This is another example. RNA is a sequence in an alphabet of size q equals 4. For each particular sequence of RNA, the molecule bends and forms a particular secondary structure that impacts its total energy. And we're using some type of physics-informed model here that is able to compute the energy for a given sequence. This is kind of a heavy thing. And we want to see if we can learn this function with relatively few samples using our Fourier transform technique. And our results show that with just 10 to the 6 samples, with a sequence of length 18, our Fourier transform is able to accurately learn this energy function. And 4 to the 18 is something like 10 to the 10. So we're looking at just a very small fraction of the point to do a pretty good job of learning this function. Now, just some concluding remarks. Fourier transforms have been useful tools for digital signal processing for the last half century. And I think that they still have a place in this new world of massive data and AI, but we'll need some new ideas for computation. And I think we can leverage ideas from compressed sensing and coding theory to help build the tools that we need. Thank you.